In section 3.1, we're going to introduce the topic of the determinant of a matrix. So let's introduce some notation first. A sub ij, we're going to let be the matrix obtained from the matrix A by deleting the ith row and the jth column. So this is going to be, if we have a 4 by 4 matrix, we're going to delete one row and one column. We're going to be left with a 3 by 3 matrix. Let's take a look at this case. A sub 2, 3 means that we are going to get rid of the second row. So that's the second row here. And the third column. And everything we didn't cross out will be part of our new matrix A23. So our new matrix is going to be 1, 2, 4, 9, 10, 12, 13, 14, 16. A new 3 by 3 matrix. Sometimes this matrix is called a minor matrix of A, but we are going to use these submatrices to determine what this determinant of a matrix is. So let's look at the definition of determinant. The determinant, which is a property of a matrix, of an n by n square matrix, A, and this is another notation that we're going to use. A is bracket A sub ij, means that all the entries of A are going to be indicated by A sub ij. The determinant is going to be denoted det of A, determinant of A, and it's given by this formula. So the determinant of A is going to be the entry in the first row in the first column, first row, first column, times the determinant of the minor matrix A sub 1, 1. So that is deleting the first row and the first column, and then looking at the determinant of that smaller matrix. Then we're going to subtract A sub 1, 2. That's the first row, second column, and we're going to look at the determinant of that minor matrix. And we're going to continue doing this all the way till we get to the end of the row. A11, A12, all the way to A1n is the first row of the matrix. We're going to multiply those by the determinant of all these minor matrices, and we're going to be multiplying each entry by -1 to the n plus 1. So what this is saying is, in this first entry we have a -1 to the 1 plus 1 here. Since that's just a positive 1, we didn't write it. Here is a -1 to the 1 plus 2. And that is a negative number, and that's where that negative comes in. And what's going to end up happening is we're going to alternate positive, negative along this determinant calculation. Another way to look at this is that this is a sum from j equals 1 to n of this -1 to the j plus 1, A sub 1j, times the determinant of that minor matrix. And again, this is going down the first row of A. Now, this definition of a determinant relies on knowing what the determinant of a smaller matrix is. But in this definition, we know how to find the determinant of a 1 by 1 matrix and a 2 by 2 matrix. We have not really talked about 1 by 1 matrices that much in this class because a 1 by 1 matrix is just a number, and the determinant of that matrix will just be the number itself. But the determinant of a 2 by 2 matrix, this A equals ABCD, is this expression that we've seen before. The determinant of A is going to be AD minus BC. And that is, we saw in the inverse, A inverse, if it was invertible, was 1 over AD minus BC times the matrix D and A on the diagonal, and then negative B, negative C. And this expression we're going to see later on has to do with the determinant in a lot of ways. And maybe this is some motivation as to why we're using this AD minus BC and this determinant. The purpose of this section and this exercise is to really understand how to calculate this determinant, to understand this definition, and we're going to look at a lot of examples in order to do that. So first example, compute the determinant of A, this 3 by 3 matrix. So given the definition, we have the determinant of A. We're going to go down the first row, and the entries of the first row are given by this 1, this 2, and this 0. That's the entries of the first row there. We're going to take each of those entries, and we're going to multiply them by some things, and we're going to add them all up. So the first thing we're going to multiply by is this -1 factor. And what we're going to do is, for the first one, since it's the first column, we're going to take -1 to the 1 plus 1. That's a positive 1. Next one, -1 to the 1 plus 2. That's going to be a -1. And then finally, we get a positive 1 at the end. And we can see that we're just going to be switching signs. We're being careful about this -1 notation because we're going to learn how to do more calculations with determinants, and it's going to be nice to be able to keep that -1 idea in mind. Then the last thing we have is the determinant of these minor matrices, the determinant of A11, the determinant of A12, and the determinant of A13. These are three new minor matrices. The first one being A11, which means that we delete the first row and the first column. So we'll do that here very quickly. If we delete the first column and the first row, we are left with the matrix -1, 2, 0, 1. And we can do that again by doing A12. In A12, we delete the first row and the second column, and we'd be left with 3, 2, 2, 1. And then finally, we're going to do the same thing with the third. That's going to be the first row, third column. We'll be left with the matrix 3, -1, 2, 0. So going down to the next step here, we have that the determinant of A we can rewrite as 1 times the determinant of this minor matrix minus 2 times the determinant of the next minor matrix plus 0 times the determinant of the third minor matrix. And now we know how to find the determinant of a 2 by 2 matrix is AD minus BC. So in this case, the determinant of this 2 by 2 matrix is we're going to take the first diagonal, -1 times 1, and we're going to subtract off the second diagonal multiplied together, 0 times 2. That's the determinant of that 2 by 2 matrix. We're going to do the same thing for this next one. We're going to take 3 times 1, and then subtract off 2 times 2. We could do the same thing for the third matrix, but note that since it's multiplied by 0, this whole thing is equal to 0. So we don't need to include it in our calculation. And then doing this calculation, we have 1 times -1 minus 0 is -1, minus 2 times 3 minus 4 is -1. This will be a -1 plus 2, which is a positive 1. So the determinant of A is positive 1. We have not talked about what does the determinant mean. We are going to talk about that later on in this course, but right now we're just focusing on how to calculate this number that's associated with the matrix. We're going to use this common notation here that the determinant of a matrix, we're not going to write as DET with parentheses. We're just going to write this as some vertical bars instead of the closed brackets. So the vertical bar on either side means take the determinant of that matrix. So the previous solution could be written down in a nicer fashion. 1 times the determinant of the 2 by 2 matrix minus 2 times the determinant of the 2 by 2 matrix plus 0 times the determinant of the 2 by 2 matrix. And then having to take the determinant as we did before. And let's look at another example here. Before we do that, let's look at something called the cofactor of A. So the ij cofactor of A is a number, Cij, and Cij is going to be -1 to the I plus j times the determinant of the minor matrix where I delete the ith row and the jth column. And we can see in our definition of the determinant that we have a lot of terms in our definition that look just like this, a -1 to some power times the determinant of a minor matrix. So what we're going to do is we're going to have something called a cofactor expansion of the determinant. The definition said that we can do it across the first row, and this is also going to be a cofactor across the first row, but we're going to show that it actually can be across any row or down any column. So first thing, a cofactor expansion across row 1. So we're going to look at this row 1 here. The 1, the 2, and the 0, just like in the determinant here, come right here, the 1, 2, 0. But now to simplify the expression, instead of writing -1 to the I plus j times the determinant of ij, we just have our cofactors, our numbers, C11, C12, and C13. This is just a nice way to help simplify the expressions so that we can deal with them in a nicer way. The theorem that I referenced a little bit ago says that to find the determinant, I don't have to go just across row 1. I can look at across any row, or I can go down any column. So if I go across any row I look at all of the entries of that row, AI1, AI2, all the way to AIN, and I multiply them by their corresponding cofactor, which is going to be a -1 to the something, so either a positive or -1, times the determinant of the corresponding minor matrix. And same thing with the determinant of A going down column J. I look at all of the entries of the column, A1J, A2J, all the way to ANJ, and the corresponding cofactors. One way to determine the -1 to the I plus j is just to simply calculate the I plus j each time, noting that it is going to alternate positive and negative across my definition of determinant. Or there is a nice matrix of signs you can use, noting that this is going to alternate positive, negative everywhere. As you go down a row, it alternates positive, negative. As you go down a column, it alternates positive and negative. If you have this idea of the matrix of signs, that can sometimes be easier to think about what are the signs going to be in the determinant calculation. In this section, we're going to be focusing on just calculating the -1 to the I plus j directly, and we'll see that on the next page. So now we're going to compute the determinant of this 3x3 matrix using the cofactor expansion down column 3. And note that this is the same matrix that we used in the previous example. We are going to get an answer of 1, just as we got before. We're just going to do it in a different way, this time going down column 3 instead of across row 1. So just as we did before, the determinant, now given with this new notation with the vertical bars, we're going to look at the 3 entries in column 3. There's 0, 2, and 1. And we're going to look at the corresponding cofactors. So note that this whole thing is the cofactor associated with the entry 0, which is going to be in the first row and the third column. This right here is going to be the cofactor in the second row and the third column. And the final thing is the cofactor in the third row and the third column. And that those subscripts, 1, 3, 2, 3, 3, 3, correspond to the subscript of the entries that we've chosen. To find the corresponding power of -1, we're going to take those subscripts and add them together. So for C13, I'm going to take 1 plus 3 or 3 plus 1. That gives me a positive 1 there. -1 to the 4th power is positive 1. 3 plus 2, because I have C23, is going to give me a negative 1. And then 3 plus 3 will be an even number, so that would give me a positive 1. And note that I have positive, negative, positive. And note that in the matrix of signs that we referenced on the previous page, if I did it for a 3 by 3 matrix, we could see that the signs from the negative 1 are going to be positive, negative, positive. Then we are left with our 3 minor matrices. We have to take the determinant of those 3 minor matrices. First one being 3, negative 1, 2, 0. Again, that's if I take the first row and the third column, I'm left with that matrix. If I take the second row and the third column, I'm left with 1, 2, 2, 0. That's my second matrix. And if I take the third row and the third column, I'm left with 1, 2, 3, negative 1, the third matrix. Then we know how to find the determinant of a 2 by 2 matrix. You take the diagonal 3 times 0, and you subtract off the negative 1 times 2. Second one, you take the 1 times 0, and you subtract off the 2 times 2. Take off, or multiply the 1 times negative 1, and you subtract off the 2 times 3. Then if we do all these calculations, note that since I had a 0 in this spot, this whole thing is going to be equal to 0. In fact, I didn't even need to put this into the calculation except to show that it will be there, but it's all just going to be 0 as soon as I see that 0 as the entry. The other two calculations, if we go all the way through those, we will get a value of 1 as an output. And again, it should be the exact same thing we got in the previous example because it's the same determinant. We're just calculating it in a different way. So another example, now let's look at the determinant of a 4 by 4 matrix. It's important to know that with this cofactor expansion, we can pick any row or any column to do the cofactor expansion. So it is going to be worthwhile to us to pick the row or column with the most zeros to make the calculation as easy as possible. We saw on the previous page that if I have zeros, then I can just get rid of that term as the whole thing will be 0. In this case, the row or column with the most zeros is going to be column 1. And we can see the entries of column 1 here, 1, 0, 0, 0, and the corresponding cofactors with them. And because they're multiplied by 0, the last 3 terms here will all just give us zeros. 0 times any number is 0. The determinant is just a number. They're all going to be 0. So we are left with just this first cofactor times 1. Note that negative 1 to the 1 plus 1 is just positive 1, so we get a positive 1 out here. This 1 times negative 1 here is just going to give us a positive 1. And then I'm left with determining what is the determinant of that 3 by 3 matrix. And again, I can pick any row or column to do a cofactor expansion. So I'm going to pick the one with the most zeros. In this case, that'll be column 1. I do the cofactor. I take the entries 2, 0, and 0. I'm not going to write down the zeros this time because I don't need to. I look at the corresponding cofactor, negative 1 to the 1 plus 1 plus 1 because I'm in the first row, first column, times the determinant of the minor matrix, which in this case is 2, 1, 3, 5, and that'll give me the final answer of 14. This would be 1 times 2 times 2 times 5 minus 3 times 1, which is 2 times 7, which is 14. This idea of cofactor expansion is very nice for small matrices or matrices with a large number of zeros, but this is not practical for large matrices. And how we're going to deal with determinants of large matrices, we're going to see in the next section. That's going to introduce row reducing first to simplify the process, and the the property of the determinant is going to be encoded in the information when I row reduce. And we'll see that in section 3.2. When we deal with triangular matrices, the determinant is a very nice thing. So here we have two triangular matrices. The first one called the upper triangular. It is called upper triangular because everything, including the diagonal above there, is grouped together, and basically everything else is 0. The asterisk means that it can be anything, including 0. That's what we mean by the asterisk. But then you have to have everything below the diagonal be zeros. And in the lower triangular matrix, everything above that diagonal is zeros, so all of our entries are in the lower triangle there. If we have this form, this triangular matrix, the determinant of A is just the product of the main diagonal entries of A. The main diagonal entries being the ones here, noting that if we're thinking about determinant, we need to have a square matrix, so there will be just one big main diagonal. So let's look at a quick example of this. We have this upper triangular matrix because I have zeros all here in the lower triangle. And because of that, the determinant is just going to be the product of the main diagonal. 2 times 1 times -3 times 4, which will give me a -24 as an answer. And that concludes this section. We're going to talk about determinants when we row reduce matrices in the next section.